All right. So going through just a little bit of review of Algebra 1 stat stuff, and then I'm going to have you try some practice problems. If you don't do well or you struggle on the practice problems, we will definitely be going over it in the following class. So please, please, please do not let it stress you out too much. Algebra 1 statistics stuff is a lot of vocabulary words. So the first one is qualitative versus quantitative. And as you can see my little cheat here, qualitative is qualities. So that's what you're looking with your qualitative data. So like hair color, eye color, opinions, that kind of stuff. So that is your qualitative data. You can't do a whole lot with your qualitative data. You can make histograms from it. So those like little bar graphs, you can make those from it. You can't really analyze too much other than figuring out what somebody's favorite item is or something along those lines. And then quantitative, that has to do with quantities, that has to do with numbers. So a height or somebody's age or their scores on a test, that would be viewed as quantitative data. So we can take the quantitative data and we can do a whole bunch of analyzing it. We can find mean, median, mode. We can figure out measures of central tendency, measures of variation or spread. You can do a lot more with your quantitative data than with your qualitative data. Next piece we have here is your univariate. That is a single variable. That means you're looking at one piece of information. You can't figure out if there's any kind of a connection because you're just looking at one thing. So maybe you're looking for the average age of students in high school, or you're looking for the average age of people who like a certain kind of soda. So our univariate means that you're looking at one thing. Bivariate means you're looking at two. You're trying to find some kind of relationship. So for example, study hours versus Regents score. That would be bivariate data. So you're comparing how long they studied for versus how they performed on the test. So two pieces of information. A lot of times your hint is you see the word and in there somewhere. So they mention this and that. Where again, whereas your single variate, it doesn't do that. You just have one piece of information. Biased. We are going to be talking about biased a little bit more. Biased is bad. That's the way I always explain it. Remember, bias is bad. They both start with B. So the outcomes of an experiment are affected by other sources. So let's say you're conducting a survey and all of the people answering the survey are your friends and family. That could be a biased survey because they could be answering the questions the way that they think you want them to answer the questions. Okay, so you're not getting the true answers, you're getting a skewed, biased answer. Or a cigarette company is conducting an experiment to figure out the harms of smoking cigarettes. There could be bias in there because clearly they want people to think that there is no harm in smoking cigarettes when actually there is. So bias is bad. That means that the data is affected and is not actually showing the true information that's happening. Unbiased means that nothing is affected. It's as random as it can possibly be. Random is a good thing. And it's not skewed in any kind of a way. Excuse me. So our measures of central tendency. So that's trying to help you figure out the center of your data. So our measures of central tendency, we start with our average, which is this symbol in your calculator. So the average is you add up all the numbers together, divide by how many of them are there. So in your calculator, remember we do stat and then edit. That's to type in your data. Stat edit types in our data. And then stat calc option number 1. That's where you get your one variable statistics. They say one var stats is the shorthand that they use in your calculator, but your one variable statistics. So what we'll find in there is we'll find things like your average, so your mean. You'll find your median, which is the middle when numbers are put in the correct order, which would be least to greatest. So we always have to organize them least to greatest. If there's two numbers that end up being in the middle, you average those two numbers together. So 1, 2, 3, 4. Let's say that's our data set. Trying to find the middle, I like to go with crossing out from the outsides until I meet them in the middle. So if I cross this one with this one, I have two numbers right here in the middle. So if I average those together, my median would be 2.5. So if we have two numbers in the middle, the median is the average of those two numbers. And then mode is what occurs the most. You can also say that there is no mode. So if every piece of data is there once, so like my data set that I just made up here, 1, 2, 3, 4, that has no mode. Every number is there once. If there is no mode, you actually have to say no mode, because if you tell me 0, that's going to be wrong. That is a data point. You have to say no mode if there is no mode. And you can have more than one mode. So like, let's say, for example, I had 1, 2, 2, 3, 3, 4. I have two modes here. I have the number 2 and I have the number 3 are my modes. So you can have more than one, you can have none, or you could have just one of them. So those are our measures of center. Those are the ones that help us figure out where that middle of our information ends up falling. So the next is the measures of variation and spread. So that tells us how different are the numbers. So you could have two different sets of numbers that end up giving you the same mean, the same median, but they actually look very different when you look at their variation. They actually look very different when you look at how far apart those numbers are. So the measures of center get combined with the measures of variation and spread so that you can really truly analyze your univariate data. You always want to look for an outlier. An outlier is a value that is very far removed from the rest of them. So like if you're looking at house prices and the houses are 125,000, 130,000, 127,000, and then all of a sudden you have a $300,000 house. That $300,000 house, that is going to be an outlier because that number is very far removed from the rest of them. So that outlier tends to skew your data a bit. It affects the mean the most. So an outlier skews your mean the most, which would then make your median, your middle number, the most accurate. Range is the difference between the highest and the lowest numbers, so your max minus your min. And standard deviation on average is how far a data point is away from the mean of the data set. So standard deviation tells us how much distance there is between the mean and your points. The larger the standard deviation, the greater the variation. So if your standard deviation value is larger, that means there's a lot of variation in your numbers. When trying to determine something like this with your standard deviation, you do need to take into account what it is you're talking about. So for example, if we're talking about, weights of baby bunnies. Baby bunnies don't weigh a lot, and there's not too much variation in their weight. They're all generally around the same weight. So if you have a standard deviation that's like 0.1 ounces, that makes sense because they're all very similar. If you have a standard deviation that is 1.5 pounds, that's not right. That's not right at all. So you have to, again, think of the context. Does it make sense to have a smaller number or a larger number? Would it work in that instance? So like if we're talking about house prices, yeah, you're going to have a pretty large standard deviation for that because those do vary a lot more than, say, the weight of baby bunnies. So context is key for that. And we have two types of standard deviation. We have a sample standard deviation. So that's where if you, instead of looking at the entire population, you look at a small portion of the population. So like if we're looking for the heights of all 10th grade students, but I only look at your class, that is a sample because I am not looking at all the 10th grade students. I am only looking at a small sample of them. Population would be if I looked at all of the students. I put these symbols in here because those are the ones in your calculator. So sample standard deviation is your SX. Population standard deviation is your theta or your omega X. Sample is the one that is used more often, especially in Algebra 1. We will start seeing the population a little bit more at this point in time in Algebra 2. And then our last thing on this one, talking about histogram. So this is our frequency histogram here. So if we take a look at all of the pieces, here talks about your frequency. Here is your measurement. These bars are always the same exact width. They are not, then it is not a frequency histogram. They also need to all be touching, which I realize if you look over here, it's not touching, Mrs. Pelkey, but it actually is. This just means that there are 0 values right here from 100 to 109. So it is actually touching. Notice we have a break in the graph because I'm skipping over numbers just like any other of our graphs that we have here. If we had a cumulative frequency histogram, move this up a little bit so you can see my quick little sketch here. Cumulative frequency histogram. Cumulative means adding everything up from the beginning. So like we're very used to hearing of cumulative snowfall. We talk about cumulative snowfall all the time. So cumulative frequency means everything is getting added in since the beginning. So it ends up looking kind of like stairs. So like this is our first snowfall. This bar here actually represents the first and the second snowfall. So it's all of the first snowfalls in there, plus the second snowfall. And then this is the first, second, and the third added together. So they keep going up. So this last bar here ends up being your total. So that is how much snowfall we had total for the season. And again, histograms only work with univariate data. So far, everything has been about univariate data. You can only have one thing that you're looking at for these ones. All right. All right, some other ones we have here, dot plots. We're going to be seeing a lot of dot plots during this unit, so we will definitely be coming back to this. But this is just what a dot plot looks like. So each dot represents one data point, and it's above that data point. So this is saying that there's 1, 2, 3, 4, 5, 6 times that the number 4 was used. 1, 2, 3, 4, 5 times that the number 5 was used. So that's what each of those dots means. Percentiles and quartiles. Percentiles is the percent of values in the data set that are less than that given. This is used a lot when you were babies, which I know you totally don't remember because you were a baby, but this is used all the time. When you're a baby, they always constantly measure your height, your weight, and your head circumference to make sure that you are growing the way that you should be growing. Now, not everybody's head, weight, and head circumference are the same numbers, but they measure those to make sure that your values are still growing at a proportionally appropriate rate. So what they do, though, is they measure your head, your body, your height, and your weight, and then they compare you to all of the other babies born on the same exact day as you. Okay, so for example, my oldest daughter, Madeline, when she was born, her height, she was in the 75th percentile. So what that means is 75% of the babies born the same exact day as her, they were shorter than she was. And so that means 25% of them were taller than she was. Okay, so it goes both ways with that. So 75% were shorter, 25% were higher. Her weight was like the 67th percentile. So again, 67% of them weighed less than she did, but 33% of them weighed more than she did. And then her head circumference was the 99th percentile. So she had a big old noggin on top of that body. She looked like a little lollipop. It was adorable. So that's what they do. Percentiles compare you to other things. So in this case, when you were a baby, they compared you to the other babies born on the same exact day as you. So as soon as you see that word, those letters "ile" at the end of it, That means you're comparing it to something else. It's not just a percentage. You're comparing that number to something else. So we then break it down into more specific quartiles, percentiles. We look at quartiles. So we got the first quartile is the 25th percentile. The second quartile is the 50th, which is also your median. And then the third quartile is your 75th percentile. We don't talk about a fourth quartile, although that would be your 100th, but we don't talk about that one at all. So your lower quartile is the bottom 25%, so that's your Q1. Your upper quartile, the top 25%, that is your Q3. Median again here, that's your second quartile, so that's your Q2. Splits it up exactly half and half. And then the interquartile range, Q3 minus Q1. This is having us look at that middle 50% of your data. All right, so middle 50% right there. That's what that interquartile range is. So we use those quartiles a lot in order to create box and whisker plots. So here's an example of a box and whisker plot right here. So as you can see, I labeled it for you. This first dot is always the min. No matter what box and whisker plot we have, that one is always the min. Your Q1 is always the first part of the box. Your Q2 is the middle of the box, which remember that's your median. And then your Q3 is the outer edge of the box. And then we got your maximum. So each part of this represents 25% of your data. So that first quote unquote whisker is 25%. Each piece of the box is 25%. So 25%, 25%. And then that right there is also 25%. Your IQR, as I said up above, that is your middle 50% of your data there. Okay, so this is just a graphic way of being able to look at your quartiles. Now, from a box and whisker, you can't really do anything else. You can't figure out your average. You can't figure out your mode. You can't figure out your standard deviation or anything from that. It's purely just your quartiles from it. But it's a nice representation for those quartiles. All right, shapes of our distributions. No, I don't want to use orange. So we've got symmetric. Now keep in mind, it's never going to be absolutely perfect. It's very rare that it's absolutely going to be perfect. But if I were to draw like a little curve over this, which we're going to be dealing with a curve a lot more this unit, we call this a normal curve. It's pretty symmetric. Both sides look pretty similar to one another. Your box and whisker plot, as you can see, each piece of it looks to be exactly the same length. So that's how we know we have data that is symmetric. Here's the part that gets a little confusing sometimes. So skewed right. If I try to draw my curve over here, this one's not quite so dramatic, but I end up with a little tail over here. So what's happening is my information would be here, but this little tail is pulling some of the information over to the right. So it's skewing the information slightly. So instead of being here in the middle, it's getting pulled a little bit this way to the right. The reason we have a tail usually is there's probably an outlier over there on the upper end of your data. So it's getting pulled this way. In our box and whisker, as you can see, this box is a little bit bigger. So that's telling us that our data is going to be skewed. It could be the whisker that is considerably bigger. Okay, but there's some aspect over here on the right side, whether it's this part of the box or this whisker, that's skewing our data to the right. So that's our skewed right. Skewed left is the same thing, only your tail is over there on the left, which again is probably your outlier. So again, all of my information would be right over here, but it's getting pulled to the left by that tail, by that little bit of information over there on the left. And again, as we can see, my box here is a little bit longer. So it could either be the box is longer on this side or your whisker is a little bit longer, but it's not all even like it was for our symmetric. And then these two we don't use really all that often, but they are noted. Uniform distribution, pretty much everything is the exact same. All of the numbers are there the exact same. The data is all there the exact same. And then bimodal, I like to think of it as two peaks. That's how we know we have bimodal data. All right, so what I'm going to do is I want you to go work on the next couple of pages. I will post the answer key for the statistical refresher and the president's children, but I want you to try the other page on your own. So the refresher stats for Algebra 2 on your own, skipping number 3. And I will write that in the assignment, but I will have the answers for the other two so you can check yourself as you are working.